Good morning, this is class 3 of our chapter Polarization. Now, this paragraph we have already discussed in our last class, that is elliptically and circularly polarized light. Suppose that you are passing a monochromatic light through a nickel prism. When it comes out of the prism, it will be plane polarized. Now, suppose that you are again passing this plane polarized light through a uniaxial doubly refracting crystal whose faces are cut parallel to the optic axis. So on entering this crystal, the plane polarized light will split into two components, that is, one is ordinary ray and the other one is extraordinary ray. Here both rays travel with same in the same direction but with different velocities. Now this we have already discussed in the last class. Now when the rays have traveled through a thickness say d of the crystal, definitely a path difference delta will be introduced between them. So look at this figure. Suppose that the amplitude of the incident plane polarized light on the crystal is A, and suppose that it makes an angle theta with the optic axis. Then the amplitude of ordinary ray vibrating along the direction PO is A sin theta, and the amplitude of extraordinary ray vibrating along the direction PE will be A cos theta. Okay. Now let us write the wave equation for extraordinary ray. For extraordinary ray, it is x equal to a cos theta sine of omega t plus delta. Similarly, for ordinary ray, we use the letter y is equal to a sin theta sine omega t. Now let us put a cos theta as small letter a and a sin theta as small letter b in the above equations. Then equation 1 will reduce to x equal to a sin omega t plus delta, and equation 2 will reduce to y is equal to b sin omega t. Now again from equation 4, y by b is equal to sin omega t, and cos omega t will definitely be root of 1 minus y square by v square, because sin square theta plus cos square theta is 1. Now again from equation 3, what will be x by a? It will be sin omega t cos delta plus cos omega t sin delta. These are very easy calculations. Now from equation 4, y by b is equal to sin omega t. So what will be cos omega t? It will be root of 1 minus y square by b square. Now from equation 3, we have already written as x by a equal to sin omega t cos delta plus cos omega t sin delta. So x by a is again equal to, what is sin omega t? We have already written it as y by b. So replace sin omega t with y by b. Cos delta is kept as such. Then put the plus sign. Now what is cos omega t? We have already written it is root of 1 minus y square by b square. So substitute that in the place of cos omega t, and then sin delta is kept as such. Now y by b cos delta, that is in RHS, is taken to LHS. So LHS will become x by a minus y by b cos delta. The one is kept in the RHS itself, that is root of 1 minus y square by b square sin delta. Now just squaring and rearranging LHS and RHS, we get x square by a square plus y square by b square minus 2xy by ab cos delta equal to sin square delta. That is equation 5. This is nothing but the general equation of ellipse. Now let us see a few special cases. That is when path difference delta equal to 0. What will be sin delta? It will be 0. What will be cos delta? It will be 1. So from equation 5, how will equation 5 reduce to? It will become x square by a square plus y square by b square minus 2xy by ab equal to 0. It is nothing but x by a minus y by b the whole square is equal to 0. From that you can write y as bx by a, which is nothing but equation of a straight line. So this means that the emergent light will be plane polarized. Now suppose that the path difference is 90, that is 90 degree, pi by 2. In such case, sin delta will be 1 and cos delta will be 0. Now what will be equation 5? It will be x square by a square plus y square by b square is equal to 1. What is this? This is the equation of a symmetric ellipse. Now this means that emergent light, when the path difference is 90 degree, emergent light will be elliptically polarized provided a not equal to b. Now if a is equal to b with path difference as 90, and suppose that if a is equal to b, then x square plus y square equal to a square. This is nothing but equation of a circle of radius a. So emergent light will be circularly polarized. So here, when the path difference between ordinary ray and extraordinary ray is 0, emergent light will be plane polarized, and we have proved this using these expressions. Now, when the path difference between ordinary ray and extraordinary ray is 90 and A not equal to B, then emergent light will be elliptically polarized. Now, path difference is kept as is the 90 degree, but A is equal to B, then the emergent light will be circularly polarized. Now, another condition. Suppose that vibration of plane polarized light on the crystal, suppose that it makes an angle 45 degree with the direction of optic axis. Then shape of ellipse will be as shown. Okay, so these are the various conditions. That is how the emergent light will look like when the path difference between ordinary ray and extraordinary ray is 0, 90, and if it makes an angle 45 degree with the optic axis, etc. Now next is definition for quarter wave plate. What is quarter wave plate? It is a doubly reflecting uniaxial crystal made of calcite or quartz, and its faces are cut in such a way that it is parallel to the direction of optic axis. Now what about its thickness? It is in such a way that ordinary ray and extraordinary ray will make a path difference of lambda by 4 after passing through it. Now the incident light will be plane polarized if it is perpendicular to the surface, and ordinary and extraordinary ray will travel along the same direction with different velocities. If the thickness of the plate is T and refractive index of ordinary and extraordinary ray is mu0 and mu e respectively, then what will be the path difference between the two rays? It will be mu0 minus mu e into T. T is the thickness, mu0 refractive index of ordinary ray, mu e refractive index of extraordinary. That is the formula only in the case of negative crystals. For positive crystals, it will be mu e minus mu0 into T. Okay, now to introduce a path difference of lambda by 4, because it is quarter wave plate, so path difference introduced will be lambda by 4. So to produce path difference of lambda by 4 in the case of calcite, it will be that is, calcite is a negative crystal, so it will be mu0 minus mu e T equal to lambda by 4. From that, what will be T, the thickness? It will be, on rearranging the equation, it will be lambda by 4 mu0 minus mu e. Now in the case of positive crystal like quartz, what will be T? It will be lambda by 4 mu e minus mu0. Now similar is the explanation for half wave plate also. Now the last sentence, if the plane polarized light whose plane of vibration is inclined at an angle 45 degree is incident on a quarter wave plate, then what will be the emergent light? It will be circularly polarized. Now similar definition, the sentence and all are same, just a few differences. Now half wave plate. This plate is also made from a doubly reflecting uniaxial crystal, and its faces, as said before, it is cut parallel to the optic axis. The thickness of the plate is such that ordinary and extraordinary make a path difference lambda by 2, because it is half wave plate, so it is lambda by 2 after passing through the crystal. In the case of quarter wave plate, it will be lambda by 4. Okay, that is the only difference. Now similar as above, to produce a path difference of lambda by 2 in calcite, what will be that is mu0 minus mu e T will be equal to lambda by 2. So T will be lambda by 2 mu0 minus mu e. In the case of quartz, it will be T equal to lambda by 2 mu e minus mu0. Another definition, retardation plates. That is, quarter wave and half wave plates, they are generally called as retardation plates because they return either ordinary ray or extraordinary ray. It is also made by cutting thin sheets of mica or quartz parallel to optic axis, and their thickness mainly depends on wavelength lambda. A particular plate can be used only with one particular wavelength. That is only disadvantages of these plates. Last session is Babinet's compensator. We know that a quarter wave plate or a half wave plate can be used only for light of particular wavelength. Now in order to overcome this difficulty, Babinet designed a compensator by means of which a desired path difference can be introduced. It consists of two wedge-shaped sections A and B made up of quartz as shown in this figure. Here the optic axis is vertical in A and transverse in B, and the outer faces of the compensator are parallel to the optic axis. That is the construction. Therefore, inside the Babinet's compensator, both ordinary ray and extraordinary ray travel along same direction with the different velocities. Now the extraordinary ray in A behave as ordinary in B, and ordinary in A behave as extraordinary in B. It is the opposite. Now suppose that a plane polarized light is incident at the point C in the figure. Then the beam will split into ordinary and extraordinary ray. What will be the path difference introduced them after passing through the distance CD? It will be mu e minus mu 0 into T1. In the case of section B, extraordinary ray will behave as ordinary ray and the path difference will be mu e minus mu 0 into T2. Therefore, the resultant path difference will be mu e minus mu 0 into T1 minus T2. Now, the crystals A and B are kept in such a way that A is fixed, whereas B can be slid along the surface of A. So, by doing this, we can vary the thickness T1 minus T2 to any value that we like. Hence, any path difference can be introduced with the help of this compensator, and it can be used for light of any wavelength. Okay, so in this session, you can just go through this Babinet's compensator, whereas retardation plates, half wave plate, quarter wave plate and all are very, very important. Then also this derivation. Okay, that is the expressions for elliptically polarized, plane polarized, circularly polarized light along with the special cases. Okay, so please learn it. Thank you.